for the introduction. I appreciate that. And thanks again for having me here. I really do enjoy giving talks, and Zoom talks are weird, but I'm going to make it work. So I'm going to share my screen because that's where my presentation is. And I hope that it works right. Give me 1 second here. I think I have to go full screen on that, and then that's not right. There we go. Let's try that. Can everybody see that?
Yes.
Okay. I'm gonna make it so it's perfect size here. I should have practiced this. I'm not very good with Zoom, so anyway. So what we're going to talk about today is some brand new research that actually hasn't even been published yet. It's been submitted, and we're in the review process. But this is actually research with my old advisor from Las Vegas, and I'm working on some other projects with my postdoc advisor as well. But this one came out first because it was very kind of short paper that was relevant to some recent discoveries, which I'll discuss. So the title is Growth of Stellar Mass Black Holes in Dense Molecular Clouds and Gravitational Wave 190521. Okay, so I was taught to explain my title slide in a few minutes because I think people get lost sometimes on the title alone. It's very important to go through and discuss each word. So growth, what does that mean? Okay, that means getting bigger, right? All right, stellar mass black holes, what does that mean? Well, that is a black hole, which is a singularity in space-time that is approximately more or less the mass of the sun, which is very massive compared to what we're used to here on Earth, but get very large in the end, something like billions of solar masses. And so we have to specify stellar mass black holes. And then growth of these black holes in dense molecular clouds. So molecular cloud, for instance, this Keyhole Nebula in the Carina complex, I think it's a southern hemisphere thing, can't see it in the northern hemisphere, but this is a nebula in our own Milky Way that is basically gas and dust and stars, more or less. And so you have regions that are a little bit more dense and you can't see through them in the optical. There are regions that are a little bit more tenuous and you can kind of see background objects, or maybe these are objects that are embedded in the cloud itself. And so what our research talks about and discusses is this idea that a black hole can grow while kind of living inside one of these clouds, which is an idea that has been discussed before, but in the context of how we've written it down, I'll show you some new stuff. So this GW190521 is a gravitational wave event, the largest to date discovered by LIGO. And LIGO is this gravitational wave interferometer that detects these ripples in space and time from these interesting events called black hole mergers, where two black holes actually coalesce into one bigger one. And so the number here is the date, so 2019, May 21st. And that was announced just a month ago or 2 months ago, whatever it was. And so we have an idea here that might be able to explain an interesting property about the masses of these black holes that maybe no one else thought about before. So hopefully it gets published soon. It was actually cited by the newest LIGO paper, so I'm very excited about that. So hopefully the referee will enjoy that. So outline of the talk is just this. So we have an introduction. I'm going to talk a little bit about what black holes are and to catch everybody up. And then I'll talk about these black holes being embedded in the molecular clouds. And then I'll talk about how they might grow, and that's through accretion in our particular model. And then I'll talk about a couple of case studies, because it's not only this gravitational wave event that was discovered that we can maybe explain these massive black holes through. And then finally, a little summary. So I will first talk about this. So in 1783, this is unknown to a lot of people. It's very interesting. Most people think, oh, Einstein, black holes, it's all within the last 100 years. But actually, this astronomer, John Mitchell, discovered his idea of a black hole 237 years ago, which I always thought was interesting. They called them dark stars back then. And so the letter that he wrote to Cavendish was in, of course, the 1700s language, very, very nice to read, kind of poetic almost. But what he's basically saying is that if there is an object in space, and that object is more or less massive enough, and the way they describe that is that it has the same density of the sun, but its diameter was 500 times more, something that they were trying to explain, that basically light couldn't escape from it, and therefore you wouldn't be able to see it. And so that's what they were going to call a dark star back then. So that was very interesting. A little bit after that, maybe 13 years, very famous mathematician, physicist, astronomer, all around cool dude, Pierre-Simon Laplace, he discovers independently, because he didn't know about that other discovery, the idea of a dark star. So he writes, again, in his 1700s language, more or less, if you have a body that's massive enough in space that it will attract, due to gravity, everything around it, and it'll be invisible to us if it's massive enough or dense enough, in more or less words. So that was kind of a neat history lesson. So we'll keep going. So fast forward 120 years basically, and we get Einstein. So Einstein is the quintessential dude when it comes to gravitational thoughts. So his idea, which was quite revolutionary, took him 10 years to develop, from 1905 to 1915. The idea that space and time are not distinct. They're one thing called space-time, and that if there is matter or energy inside this space-time, then I'm going to steal from physicist John Wheeler the way to explain this, that the matter-energy content of the space-time governs the curvature. So if there's something that's massive sitting in space and time, it's going to curve the space and time around it. So it's going to cause all sorts of interesting effects. And this doesn't work as well as a PDF, or in a PDF. I have to scroll down here, but the curvature itself, so if you have some region of space and time that's highly curved, it's going to inform how the matter and energy are actually moving through that space-time. So you can see just from that statement, it's a very nonlinear process. That if you have an object that's quite dense and massive, that it's going to create this space-time curvature. And then if you have curvature present, it's going to tell other matter how to move around. And so that gets very interesting when the masses and densities are very high. And of course, that's going to be the case in a black hole, which I'll discuss. So just an interesting thing to keep in mind, what kind of this black hole idea is. So, oh yeah, one more slide here, or one more equation. So in the end, Einstein writes down his field equations. It looks like one equation, but it's 10 equations, because this is a tensor equation, and it basically tells you on the left-hand side, this is the curvature of space and time, written in some compact way with different metrics and tensors. And then on the right-hand side is all the energy and matter that you might have that you can somehow write down in a neat little form called the matter energy or stress energy tensor. And so basically this equation is very nonlinear, is extraordinarily difficult to solve, 10 equations here, and only in cases of high symmetry, or if you're numerically solving it, can you get something that even makes sense. And so it's a very interesting idea, of course, and what's really cool is that you look back on these dates. So we got kind of the end of 1915. In fact, the main paper, I think, was December 1915. basically 30 days after that paper, kind of 2 months after the initial kind of papers Einstein was putting out there, this dude Carl Schwarzschild, he's super cool. So he's on the front lines of World War I, doing like ballistics calculations, and he somehow gets hold of his of Einstein's papers, and then he goes through and solves the Einstein field equations, which I was talking about right before, and he solves them for the very particular case of a spherically symmetric static mass distribution. And so what does that mean? So that's basically if you have a spherical mass sitting in space, nothing else around it, for instance, the Earth or the sun or a black hole, as we'll learn, that if you go through the equations and plug in that kind of initial condition, I would call it, then you can create you can solve these equations and find the solution. So in the end, you get a solution that is a singularity. That's what we call it today. I think, yeah, they knew about it back then. I think they call it singularity as well. But basically, you get this object that has what we call the Schwarzschild radius. And so that is kind of the distance from the singularity at which, even if you were shining a light beam, it wouldn't escape. And so this is this black hole idea. And so the estimate here is if you have one of these objects that's the mass of the sun, so a little m with the little circular symbol down there, if it has the mass of the sun, then the Schwarzschild radius of that object is about 3 kilometers. So if you compacted the sun down into a black hole, it would only be 3 kilometers across, which is kind of interesting. If you do that for the Earth, I think it's 1 centimeter, because the Earth is a lot less massive than the sun. So here are some fake quotes. We're in the realm of fake news here. I'm pretty sure gravitational waves exist. Albert Einstein, 1915. So this is an interesting point. When Einstein solved his equations, wrote them down, he found himself that there was a wave solution to the equations. And that wave solution would be ripples in space and time that would propagate out at the speed of light. And so it was a very, I guess, it was a very new idea and a very strange idea that space and time could be rippled, and that ripple would propagate out exactly at the speed of light. That was a very, I guess, hard to swallow thing back then in 1915. And so Einstein himself was actually unsure of the, I guess, if that solution was correct. And so there's actually a big debate about it for a couple decades. I think the final nail in the coffin was in the 50s or 60s, something like that. And so I put the fake quote on there because it's just funny. And then Schwarzschild was like, hey, these things called black holes exist. That's also a solution to your Einstein equations. So that's also not a real quote. But it's a very interesting thing that now these two new phenomena, which no one really thought about before. I mean, there was this stuff in the 1700s about these dark stars, but it was kind of forgotten to history. No one really cited those for those 100 years that was in between those two discoveries. And so LIGO, which is a very cool place, announced in 2015, I guess they announced in 2016, but discovered in 2015, the very first proof of gravitational waves and their existence. And so another fake quote here, indeed, gravitational waves exist. So this is kind of neat. I stole this picture from their website, credits down there, but this guy's standing on top of the two tubes of this interferometer, which is taking laser light and bouncing between this 90-degree angle, 4 kilometer long arms, and then combining the light and then analyzing the signal. Very easy way of compacting 40 years of research. But in any case, when a gravitational wave passes through the Earth or passes through this detector, that the length of those arms should change by a very small amount, and they should change in a very predictable way according to how this gravitational wave affects the space and time that is present in these 4-kilometer arms. And so the prediction was that if these two black holes are coalescing and merging into one, that they would create a bigger black hole, and in the process emit these gravitational waves, and those waves would create a signal that was detected. And so here there are 2 detectors, one in Washington and one in Louisiana, and their signals are overlaid here with a time delay, because I think it got to the Hanford one, which is in Washington first, and then it propagated 9 milliseconds later to the Livingston, Louisiana one. And so there's a perfect kind of correlation of those signals, meaning that it's probably real, and there was a lot of data analysis that went on to make sure it was real, and indeed it was. So that was very cool, because that was right when I was in grad school, and that was kind of the first proof, definitive proof, that black holes existed. And so not only the gravitational waves, but this particular signal had to have come from black holes merging. There was no other way to create that. So very cool. And
Wow.
that's, yeah, a lot more have been discovered since, and Dr. Summerscales can talk to you about that if you ask her. But in any case, this is some new stuff that came out from their group, which is all of their discoveries of black holes in one plot. And so on the y-axis here, it's not labeled, but this is solar masses of the black holes. And then these are just kind of laid out. There's no x-axis. It's just showing the different masses here. So what we're going to be focusing on is actually this system right up here. So we've got this huge final mass here of the product of 2 black holes that were merging. That one was 66 solar masses, best estimate, and one was 85 solar masses. And so the reason we're going to focus on that is that prior to this discovery, it was kind of more or less not assumed that you could create very easily a black hole of those masses. And the reason for that is that we have these stellar evolution codes. So we have a whole theory of how basically a region of gas can compact down into a star, and then how that star turns on its nuclear burning in its core, and then how it uses up all of its fuel, which is hydrogen and helium, et cetera, and how those particular, I guess, yeah, a bunch of different gas physics involved in that, and how that can kind of get you to a particular mass star. And then if you have a particular mass star, at the end of its life, it's going to go supernova if it's massive enough. And if it does, it's going to blow away a lot of the material. And if it blows away too much material, what's left is a black hole. Maybe it's only 10 solar masses, right? So it's not very big. And so those old models were basically, it was difficult to, at the end of a star's life in our computer codes, to create a black hole that was, say, 80 solar masses, right? And so there's something called the pair instability supernova gap, and that's the reason for that. And I won't necessarily go into that, but basically there's some interesting physics with creating electron-positron pairs that decrease the pressure inside of a very massive star that cause it to have this interesting supernova. And in a particular mass range, something like 55 to, I think 100, something like that, solar masses, a black hole probably won't form from that. And so, yeah, we were very confused when that result came out. It's like, how do you get a black hole that's that big? So that's one of the main things that we're trying to explain. And turns out there's a lot of interesting research in the past few months that show that there might be ways to overcome that particular constraint from the different models that the stellar evolution codes that we're using. So in any case, we might be able to explain it as well. Who knows? So I'm going to go on from that. This kind of shows it in a little bit clearer way. So this is, again, kind of just the same type plot where you have the black hole masses and these different events. So it's just not as many plotted here, so we can see it more easily. So the system we're focused on is this one that was recently announced as GW190521. So our idea is that, can we create, through a different means other than stellar evolution, the standard stellar evolution, a black hole that is something like either this one, which is 66 solar masses, or this one, which is like 85. So is there a way to create that? Okay. Well, there are only a couple of ways that black hole can grow. And so one of them is through mergers. And so you can have a lot lower mass black holes get close enough to one another that they start spiraling into each other and eventually merge, and they can create bigger black holes. All right, perfectly legitimate. In fact, that's probably the explanation for this system, but more research will tell us. There's other ways, which is if the black hole is, say, orbiting a bigger star, a single black hole orbiting a bigger star can, say, gobble up material from that star in what's called an X-ray binary, and it can grow that way. Or our idea is that we have two separate black holes, each of a little bit lower mass, which is kind of permitted in the standard stellar evolution codes. And those black holes will accrete matter from the interstellar medium at a rate that basically can maybe explain these bigger mass black holes. So who knows which one of those is correct? There's not necessarily an easy way to determine how a black hole got its particular mass unless you saw it actively gobbling up something. The only way for sure that we know a black hole grows is that they're merging, and two of the smaller ones come together and make this bigger one. So that puts out the gravitational wave signal, which we've detected and we can detect now with LIGO. And yeah, so that's the only way that we for sure know. And then there's some accretion in the X-ray binaries that we can pretty much infer the accretion rate and show that maybe it's growing a little bit, but probably not enough to explain. So yeah, so going forward with my idea here is that we have a black hole embedded in this dense molecular cloud. So I'm going to scroll up real fast to the very first slide. So that's one of these molecular clouds. The regions that are quite dense are actually not dense compared to earthly standards, but for space standards, they're very dense. They have something like 100,000 particles per cubic centimeter. That would be like the best vacuum, better than the best vacuum ever created on Earth. And so, it's really not dense compared to what we think, but yeah, they're dense relative to other things in space. And so in those dense molecular clouds, our claim is that a stellar mass black hole can grow its mass noticeably through what's called Bondi accretion. So it's kind of the classic calculation of how a black hole can accrete material in a spherically symmetric way. And I'll explain a little bit about that in the following slides. But if it's embedded in one of these molecular clouds, and the other, I guess, constraint is that it is moving slowly through the cloud. And so there are various ways a black hole can be moving quite quickly through say, the galaxy. Most of that is just because it's orbiting within the galaxy, just like everything else. And within the galaxy, everything moves at a particular rate, depending on the radius away from the center of the galaxy. And so you can have stars or objects moving at multiple kilometers per second, which is pretty fast. And what we don't want is something going at hundreds of kilometers a second, which is totally possible in our galaxy. And so we're going to have to, say, constrain that somehow. And so I'll explain that a bit. But basically, you have to have a slow-moving black hole going through this dense cloud. And in that case, it'll accrete if it's there for a very long time. So I wouldn't say it's contrived, but it's a very difficult situation to be in. A black hole generally is in probably a low density environment. A black hole generally will be moving quicker than, say, a few kilometers a second. And if it is moving that quickly, then most likely it's not going to stay in any given area for a long period of time. So how do we do that? So I'll explain that. So the model kind of provides a challenging but new channel for formation of stellar mass black holes. If it's possible that these things are kind of slowly moving and accreting, then maybe they can create these black holes that are a little bit more massive, and therefore can explain some of these recent observations of higher mass black holes. So we're going to discuss how that kind of affects or applies to that gravitational wave event. And there was also this other interesting system called LB1, and I'll talk about that. But it's a black hole that was discovered through its accretion rate of a star that's orbiting it. So it's a black hole X-ray binary. So you got a black hole and a big massive star orbiting, and then the black hole is kind of gobbling up matter from that. It was initially claimed to be much more massive, and I'll discuss in a bit maybe why it's not really actually a black hole in that system. People think that maybe the data analysis was wrong there, but we show that it might be possible to explain that one as well, if it is indeed a real observation, not fake. So, all right, so let's define these terms. I think I talked about it a little bit in the beginning, but a molecular cloud is just the region of high density, and depending on what type of molecular cloud or if it's near a star or not, it could have low to high temperature. And so this high density, we're saying something like 10 to 100,000, say, protons per cubic centimeter. So normal interstellar medium is lower than that, but you can have these high density regions, and that's where typically stars will start forming, etc. If there is no star formation going on, the temperature is like 10 Kelvin, so it's very, very close to absolute zero. So kind of this cold gas that's not doing much. But if you have some stars around, most likely through different equilibrium gas physics processes, that you're going to get something like 10,000 Kelvin or higher, depending on which type of cloud you're talking about. So again, we're talking about a very kind of specific subset of these clouds. So we want high density, but relatively low temperature, although the effect is not dependent on the temperature so much, which I'll talk about. Okay, and so a black hole can exist in one of those clouds for an extended period, maybe. I'll talk about it. And then it could accrete. So if it accretes, it's in good company, but the problem is, has to accrete at a big enough rate such that we can explain these. So what we went through in the literature is kind of a long history of people talking about how molecular clouds kind of form and interact even within the Milky Way or other galaxies. And so the typical lifetime for one of these clouds is actually what we're going to call a free fall timescale, and it's a very low number. So free fall timescale means the following: that you have kind of a blob of gas, however big it is, say it's 10 to 40 parsecs across, so something like 100 light years across, which is typical size. You can calculate kind of the average density of that ball of gas, not really ball, but just region of gas. And then you can do a simple calculation which shows that it should be gravitationally attracted to itself because it has mass. And so things that have mass attract other things that have mass. And so just like you're attracted to the Earth, these regions of gas are all attracted to each other, and that they're going to free fall in some relatively small time scale. In fact, too small for our model. And so the time scales would be dependent on the square root of the 1 over the square root of the density. And so the higher density clouds, which is what we need for our accretion, are actually going to live, if we take it in this classic sense, for a smaller amount of time. And so If the clouds don't live very long, then they can't accrete very much, or the black holes that are embedded in there can't accrete very much. And so that's kind of detrimental to our model. And so we did a big time literature search, and we found some interesting papers that talk about the molecular cloud lifetime in a different way. Not just that it, starts out as a gas cloud and then just collapses on itself in some fashion. Really, they're embedded in a galaxy. And so the black hole is not only attempting to collapse because it's gravitationally attracted to itself, it's revolving around the galaxy. There's also interesting effect about shear. So if you have a relatively large gas cloud, then the part that's closer to the center of the galaxy will actually be revolving around the galaxy quicker than the part that's further away. And so as the cloud is trying to collapse in on itself, it could actually be kind of ripping apart due to that effect. And so in addition to a bunch of other interesting things, is that in the end, you can have a molecular cloud that in the simple calculation probably would survive for 5 million years, that actually survives for much longer. In a typical timescale that this paper from 2018 cites is something like 20 to 60 million years, and dependent on all these different galactic effects, maybe it could live for, in other galaxies, for something like 100 million years or even 200 million years. And that's good for us because we want a cloud that kind of survives for a long time so we can gobble up that gas and grow the black hole. Okay, so that's the idea, is that we have this long-lived cloud and we're going to be accreting the material from it. Okay, so a little bit about black hole accretion. So this is going to be a little bit of math, but I know the mathematicians probably will yell at me for my simplistic versions of these equations, but and without proving anything, I'll just write it out. You can find all these papers in the literature. The classic paper is Bondi 1952, where he discusses that if you have this compact object, so we'll say black hole, then it can accrete in a spherically symmetric way matter that's surrounding it. And so we're going to have, for our particular black holes, this competition actually. So dmdt is just going to be the rate at which the mass of the black hole grows because it's gobbling up this gas. Okay, this is the rate of increase of the mass of the black hole. And then over here, it's kind of a fight. So there's a fight between what we're calling the Bondi-Hoyle-Littleton accretion rate, or Bondi rate for short, versus the Eddington rate. So a little dot above just means time derivative. Okay, so what is that? All right, let's go to the next little thing here. So if you have matter that's accreting onto a black hole, so it's just free falling onto this dense object, it's matter, and so things can happen to matter that can't happen to, say, black hole. So in this particular case, the thing that happens to matter when it's falling onto a black hole is that it can heat, the temperature of that gas can heat up, so it can get hotter. And if it does that, it radiates, and it radiates light. And so if this gas that's falling into a black hole gets too hot and it radiates too much, then the light that's coming off of this heated gas is going to be pushing back against any of the other gas that's trying to fall in. And so there's this kind of interesting limit called the Eddington limit and the Eddington accretion rate, at which if you have light being created by the infalling matter, it's going to be pushing back with a certain pressure on this gas, and there's a limit to that, and that's something like 10 to the minus 7 solar masses per year, falling onto a black hole that's 10 solar masses. Okay, so in the end, the total accretion rate is going to be kind of a fight between, if this Bondi rate, which I'll write down here in a second, is too large, then actually it converts back to this Eddington accretion rate, because all this light is pushing back on the matter that's falling in. You can't get past that. There are ways to get past that but I won't discuss all that interesting stuff here. But the Bondi rate is going to be dependent. So here in the accretion, or the Eddington accretion rate, the Bondi, or the rate is dependent linearly on the mass. And so as your mass increases by a factor of 10, that accretion rate, kind of that limit, increases by a factor of 10. Whereas this Bondi accretion rate, which I didn't derive, but just show the result here, is dependent on the square of the mass. And so if your mass gets too big, it's actually going to approach this Eddington rate, and then your total overall accretion rate should kind of default to this Eddington rate. And in the simulations that people do, I don't do simulations, but in simulations that people do in various scenarios of different masses, different, say, gas densities, different temperatures, etc., it's generally true that kind of the maximal accretion rate is Eddington, unless there's some interesting, I guess, constraints. But in any case, the Bondi rate is actually relatively similar to that rate. And so it's something like 10 to the minus 8 solar masses per year. So that means that in 10 to the 8 years, you could grow by a solar mass. And so this depends on the velocity of the black hole through the interstellar medium, or the molecular cloud that we're talking about. And so if you have so it's velocity to the minus 3, so if you have a black hole that's moving relatively slowly, then it's not gonna, or this rate is gonna be a lot higher, so that's good. But if it's moving, say 100 kilometers a second, then that rate is gonna go to 0, and you won't really get to a place where you can grow the black hole very much at all, which is undesirable for our model. But in the end, if it shows that it can't grow, then it can't grow. No big deal. Okay. So as long, basically, as if you're going at 10 kilometers a second, if the black hole is moving through this molecular cloud at 10 kilometers a second, then if the density of that cloud is 10 to the 5th particles per cubic centimeter, then this limit, this Eddington limit, does not kick in until the mass is 150 solar masses. So that's perfect for what we're trying to explain with that gravitational wave event, because even the final mass of that, I think, is only 140 or 150 solar masses. So to try to explain all the lower mass black holes that might have accreted to get to the initial black holes of those particular, for that particular system, then our model at least is relevant. So the constraints are, we have to be relatively dense, 100,000 particles per cubic centimeter, and going, say, 10 kilometers a second. So the other question is, all right, so if a black hole is going 10 kilometers a second, then it's going to kind of traverse the molecular cloud in some amount of time. So if it's going too fast, again, it'll just escape the molecular cloud. It's no longer accreting very, very much, and that kind of kills the model. But basically, as long as kind of the escape velocity of the molecular cloud, so this is the effect of, if you jump, you're always going to fall back down. I mean, unless you jump, 8 kilometers a second, and then you can escape the Earth, right? Same type of effect. If the black hole is kind of in this cloud, even if it's moving quickly, if the molecular cloud kind of has this escape velocity that's relatively high, then the black hole is kind of going to be, excuse me, orbiting inside this molecular cloud in some way, and maybe it can stay in there for longer. So that's good. Kind of the limit for that is that the escape velocity is probably, for a molecular cloud that we're talking about in our model, something like 1 million solar masses, and the radius is something like 20 parsecs, or about 60 light years, then this escape velocity is pretty high. And so a black hole that's moving at 10 kilometers a second will most likely at least stay in the cloud for a long enough period of time. So that's the idea. So in the end, what we showed is that assuming all these constraints could be true, which it's definitely not true for a lot of molecular clouds and a lot of situations, but it could be true in a small number of them. And if it happens to be true, then this plot shows how these black holes would grow. Okay, so on the x-axis we have time and in years, and so it's a log plot in x, and so here the vertical line is 20 million years and here it's 60, and that's the limits I was kind of talking about from before, from that paper on the molecular cloud lifetimes. So in this kind of regime here is going to be how long that molecular cloud lives, and therefore how much our black hole can grow. On the y-axis is the fractional mass increase of the black holes. So if you have, for instance, delta M over M, so that's the kind of final mass of the black hole versus the initial, or minus the initial over the initial. If fractional mass increases 1, that means you've doubled in mass, right? So you basically have added the initial mass to the final mass, and therefore, yeah, 1 here is double, here I guess that would be triple. So what we show, and the solid lines are the Eddington limit. So if this thing was accreting the entire time at that higher Eddington rate, then it's going to grow a lot more over time. So that's the 2 solid lines. The 2 different situations are 2 different mass black holes initially. And so this one is a higher mass black hole, this one's a lower. And so if it accretes at this Bondi rate, that's the dotted line, it can still actually grow a lot relative to, say, a different situation, which say the density was lower and whatever, it wouldn't grow. But you can see even for a lower mass black hole, we can get to fractional increase in the mass. I think it's something like, let's see, it's 10%, and here I think it was a 57% or something. I'll have to go look back in my paper for the exact numbers, but it's possible in kind of this relatively difficult molecular cloud to have, that this black hole could increase in mass a good amount. The other thing, or the other plot that we have in the paper is this one, which is similar, but it's just showing the mass and not the fractional mass increase. So it's the same data, just plotted in a different way. Again, we have the y-axis the x-axis is time, and the y-axis is a mass. So what we show is that if you want to create the black holes in the LIGO system GW190521, which have an initial mass of 66, which is this horizontal line, and 85, which is that horizontal line, solar masses, then if you start off with approximately a 41 solar mass black hole and accrete in this molecular cloud, then you can actually reach 66 solar masses relatively quickly. So this is 2, 3, 4, now 60 million years here, right? And so you could actually create this black hole. Or if you were starting with a higher mass black hole, and I think this one is 48 solar masses, then again, by the time you reached about 60 million years, you could grow to 85 solar masses. So it is possible, again, assuming all these constraints, that you could grow to these masses. And so that's actually pretty neat, because then you don't have to really rely on these stellar evolution models that are difficult to explain, these bigger mass black holes. You can say, well, these lower mass black holes are perfectly explainable in the standard stellar evolution models, and they get created in some process, and then they end up in a molecular cloud. Either they formed there to begin with, or they've migrated through the galaxy and found another one to accrete. And then those can kind of accrete this mass here and eventually, relatively short time, accrete to get to these masses that could explain the gravitational wave event. So we're not saying that this is the way that it happened, we're just saying it's possible. And the referee on our paper actually came back with a couple good points that it might not be possible in certain ways, but we're replying back to the referee and saying, actually, you missed this paper, and what their point was that the rate just wouldn't be high enough because of what's called feedback. So this was an effect that I was kind of talking about earlier, which is as the black hole accretes, it heats up the gas surrounding it, and then that light that gets created by that hot gas can push back on any future accreting gas and therefore lower the accretion rate. But actually in a lot of simulations, they've shown that if the black hole is moving through that gas instead of just stationary, that you're going to have some interesting effects with kind of a wake that forms, just like if you're in a boat and the wake that forms behind the boat on the water. You get kind of an interesting wake of gas behind the black hole as it moves forward through the molecular cloud, and actually the accretion rate will maybe even increase over the classic Bondi rate, so that would even be better for our model. So we're probably going to be published soon based on that point. I just have to finish writing all the corrections, so that should be fun. So for the particular case studies we're talking about, which I already kind of went over a little bit, for this gravitational wave event, both of those were relatively massive black holes, 85 and 66 solar masses. And we showed kind of in our paper that if you start off with, say, a 41 or a 48 solar mass black hole, then actually you could grow to these bigger black hole masses in a relatively short time, and then eventually you could kind of have those near each other, and they would eventually merge to form this event, which was actually, it happened very early on in the universe relative to, say, nearby in the Milky Way. And so that's an interesting case study. And then there's the system LB1 that is pretty controversial because the initial data analysis was shown probably to be incorrect. But the system was supposedly a 70 solar mass black hole that was orbiting a giant B star. And in that particular system, they discovered, well, they already knew about it through X-rays because it has an accretion disk, and those X-rays are being created in that accretion disk, and we can observe that. But they did some other data analysis on the system and showed in their way that maybe it's a 70 solar mass black hole and not regular stellar mass. And then people came along and said, oh, you know, you did that wrong. You did that so wrong. And they went back and forth. There were a bunch of papers that came out on either side of the aisle. And in the end, the original group kind of agreed with a lot of the additional papers that came out and said, you know, hey, probably not a black hole at all. And so, but in any case, if it is a black hole that, you know, is that massive, we can explain it in our model, which is interesting. So I think I just talked about that. And kind of the summary is that we kind of outlined this scenario for black hole growth, and it's a little bit contrived, but it's possible. And so these higher mass or lower mass black holes can eventually grow into bigger ones. So I'll just leave that up. That's the final slide. So thank you. Any questions?